a really useful property of enthalpy. And this is something that we call Hess's law, and you might have heard about it, you might even have done problems about Hess's law. If you have a reaction that occurs by more than one route, enthalpy is the same whichever route is followed. What it means is that enthalpy depends on the state of the reagents and the products and how many moles of each are involved in the reaction. But what happens for the reagents to become products does not affect the enthalpy of the reaction. It's only what reagents are in what states you have them, and the quantity you have them, and what product you are making, the quantity of the product you are making, and the state of the products. That's what is important. That's what determines the enthalpy of the reaction, not the route. So if you can produce the same product or products in two different ways, as long as the reagents and the products are the same and the proportions are the same, that enthalpy will be the same. So if you look at this reaction, the first reaction, you have hydrogen gas, 1 mole of it, that reacts with 1 mole of iodine in solid state, and you form hydrogen iodide in gas form, 2 moles of it. This reaction, it's an endothermic reaction, that's what the plus means, and it requires 53 kilojoules of energy for the reaction to happen. You could think of this reaction as having 2 steps. One, that you have iodine in solid form and it becomes iodine in gas form. And then you could have iodine in gas form react with the hydrogen in gas form to produce the 2 moles of hydrogen iodide also in gas form. And when you do the reaction and both reagents are in gas form, the hydrogen and the iodine, look that the reaction is, well, it's easier. It's easier because you have 2 gases reacting rather than a gas and a solid. And actually the reaction is exothermic, it's slightly exothermic. While if you had made the reaction with the iodine in solid form, the reaction is endothermic. But transforming the iodine from solid to gas form is an endothermic reaction, 62 kilojoules. So when you add up all these, you have hydrogen in gas form plus iodine in gas form plus iodine in solid form. That gives you iodine in gas form and 2 moles of hydrogen iodide in gas form. And you look, okay, well, I have an iodine in gas form here and here, and that's the only thing I can cancel because the others are not the same. The iodine is in solid form, cannot be cancelled with anything. The same with the hydrogen in gas form, the same with the 2 moles of hydrogen iodide. And if I look at this and I think, okay, what did I do with the equations? I add them up. So if I add up plus 62 minus 9, because it doesn't matter the route to go from the hydrogen ion, the iodine, to the hydrogen iodide. It's a solid or liquid. It doesn't matter what happens in the middle of the reaction, what actually happens. What matters is the state and number of moles of the reagents, and the state and the number of moles of products. And as long as the path from A to, A and B are the same, the path you take to go from A to B doesn't matter. The enthalpy change will be the same. Hess law is quite a useful law because, well, it can save a lot of time and effort. You can calculate any change of enthalpy for any reaction if you know of other reactions that will give you those reagents and those products in those states. And sometimes there are reactions that you might not be able to take the direct measurements using a calorimeter, for example, either because the chemicals are dangerous or maybe just very expensive, but for example, toxic chemicals or particularly dangerous chemicals, or changes in enthalpy that are very small. So the change in temperature is very small, the amount of heat being released or absorbed is very small, and then you make a lot of error when you're measuring it. But if you find tabulated data of other reactions that involve those chemicals in those states, and you can combine them to make your target thermochemical equation, then you can calculate the enthalpy of the changing enthalpy of that reaction. So, although it is a little bit beyond the scope of this module, this series of videos, sorry, I would like to just ask you if you would like to have a go at this exercise. You've got here this reaction. So that's phosphorus in solid form. They react with 10 moles of chlorine gas to produce 4 moles of phosphorus pentafluoride. And I'm asking you to calculate the change of enthalpy of that reaction. And I'm giving you 2 reactions to play with to obtain that reaction that they involve all the reagents and products. So could you calculate the enthalpy for this reaction, our target reactions, using the 2 reactions that I'm giving you below? Stop the video now, please. Let's have a look and see how we would tackle this exercise. The first thing I'm going to identify is where my reagents and my products are in the reactions I've been given, and if they're in the right quantity. So phosphorus in solid state, P4, I have it in the first equation, and it's in the right state, and it's in the right quantity, 1 mole. Then I tackle the chlorine. The chlorine, I need 10 moles of chlorine, and it's a reagent and in gas form. And if I look at here, I've got chlorine here, 6 moles and in gas form, and 1 mole in the second equation, also Cl2 and in gas form, which we don't know that up to 10. So I need to do something so that amount of chlorine adds up to 10, which is what I'm aiming for. But let's leave that for a second. Let's have a look at my product. My product is phosphorus pentachloride, PCl5, and I need 4 moles of it. And if I look at the equations in the second equation, I've got phosphorus pentachloride. It's the same compound in solid state, it's not in the right quantity. But that's okay, because I know that, enthalpies are associated with the number of moles you produce. So if producing 1 mole of phosphorus pentachloride releases minus 124 kilojoules of energy, if I need it, I can multiply this by 4, and I will produce 4 moles of phosphorus pentachloride. That's okay. So instead of writing PLCF, that 4 applies to the whole equation. So I need 4 moles of phosphorus trichloride in liquid form. I need 4 moles of Cl2 in gas form to produce 4 moles of phosphorus pentachloride in solid form. And I have the equation on the top that I didn't have to do anything to it, because it already had the right quantity of phosphorus that I needed. So I just write it as it is. I haven't done anything at that equation. 6Cl2, also in gas form, and I form phosphorus trichloride. So this one, I haven't done anything with the equation. 1278.8. I haven't done anything with it. The other one I have multiplied by 4. So I put this here just not to forget. And now I look at it and I add them up. And I can spot straight away, hopefully you can spot straight away, that 4 moles of phosphorus trichloride, which I don't want. I want them to go away, and I'm hoping it will go away at some point, because that would be a problem. But I'm keeping my faith that it will sort itself out, because the other compounds sort themselves out. Phosphorus in solid state and 6 moles of Cl2, and as products, I've got 4 moles of phosphorus pentachloride in solid form, 4 moles of phosphorus trichloride in liquid form, and that's it. And then I look at it and I say, well, I've got here 4 moles of phosphorus trichloride that are in the reagent side that can cancel the 4 moles of phosphorus trichloride in the product side. And I see that I've got 4 moles of chlorine and 6 moles of chlorine, and I can add them up, and that gives me 10 moles of chlorine. So 10 moles of chlorine, and then in gas form, 1 mole of phosphorus in solid form gives me 4 moles of phosphorus pentachloride in, again, solid form. So I have successfully achieved the target equation, and I just need to do the calculations with the enthalpies. 124 minus 124 times 4 minus 1278.8, and assuming my my maths have not failed me, the enthalpy of the reaction is minus 1774.8 kilojoules.